We are going to see some examples of how to find Taylor and Maclaurin polynomials of some functions. Later on, we are going to see why these polynomials are actually useful. Let's write again the definition of the Taylor polynomial associated to a function at a point of degree n. So Pn of x is going to be given by, we're going to have some coefficients. We're going to be summing from 0 to n. And then we're going to have x minus c to the power of k because we are doing it around c. Right here, function f at x equals c. We now need to say what the coefficients are. For finding the coefficients, we need to find the derivatives of the function. So we need to make sure that the function has derivative of at least order n, up to at least order n, and then we need to evaluate that at c and divide by k factorial. For our first example, we are going to consider the function e to the power of x at x equals 0. So we're going to be actually talking about the Maclaurin polynomial, and let's just say we're doing it for degree n in general. So we're going to need to know what are the derivatives of the function evaluated at the point 0. But that's our lucky day. Any derivative of this function, we can write n greater or equal than 0, and then this 0 derivatives means just the function, is the function itself. So when we say that we want the kth derivative evaluated at 0, we just want e to the power of 0, which is 1. So that means that the ak, the coefficients we're trying to find, they're just 1 over k factorial, which means that in this case, our polynomial is going to be summing from 0 to n, x to the power of k over k factorial. Notice that we say that the series associated to this function is exactly the same, x to the power of k over k factorial, just well, as a series, infinite. Yeah, so well, because that's how we actually define the Taylor series. This that we have over here is a Taylor polynomial, well, Taylor Maclaurin, because Maclaurin is a special case of the Taylor polynomials. So this is a Taylor Maclaurin polynomial. And then if we want to consider the Taylor or Maclaurin series, well, we are just considering the limit as n approaches infinity of the end Taylor or Maclaurin polynomial. So this example came together with a new definition, and even more, we checked that the series we talked about at the beginning is actually the one associated to the function e to the power of x. Let's see one more example. And actually, since we already defined what are the Maclaurin and Taylor series, let's find what is the Maclaurin series. So when I say Maclaurin, I say that here the point we're considering is at 0 for the function, and we want f of x to be the sine of x. So, well, first of all, notice that the sine has derivative cosine, and then derivative negative sine, and the derivative negative cosine, and then back to sine. So that means that we can consider the derivatives of this function up to any order we wish, and that's why we can find the Maclaurin series. We just have to be patient and write what actually those derivatives are, evaluated at 0. The function itself, evaluated at 0, its sine at 0 takes the value 0. The first derivative of the function is the cosine of x, and if we evaluate this at 0, we get cosine of 0, which is 1. For the second derivative, we are going to have the derivative of the cosine, which is negative sine of x, And when we evaluate this function at 0, we get the value 0 again. For the next derivative, the third one, we have derivative of negative sine, which is negative cosine. And when we evaluate this at 0, we get the value negative 1. Okay, don't worry, you will see that we're not going to keep doing this forever, because if we move on to the fourth derivative, the derivative of minus cosine of x, that's just sine of x. So we are actually back to the starting point. Yeah, we were back to the original function. So we know that the derivative at 0 is 0, and then the cycle is going to repeat. So the cycle goes 0, 1, 0, negative 1, 0. And we can write this in the following way. We can write at the end derivative of the function at 0. We can say this for n greater or equal than 0, and then if n is 0, we mean the function itself is going to be, well, it's going to be 0 when n is a multiple of 4. So for the values 0, 4, 8, and so on, it's going to be 1 if n is a multiple of 4 plus 1. So for the values 1, 5, 9, and so on. Next it comes 0 again. This is for the values 4, multiple of 4 plus 2. So we could have to say that for the even numbers is 0. But I want to respect this cycle of 4. And for the last one, we get negative 1 when we consider n to be a multiple of 4 plus 3. So let's write what our series is going to be. We are going to be summing from k equals 0 to infinity. And we are going to have only the odd numbers, the odd indices giving me something non-trivial. So I'll write x to the power of 2k plus 1. Yeah, again, the reason why I don't want to have the even ones is for the even ones, the coefficients are going to be 0. Well, we are also going to have dividing 2k plus 1, all of that factorial. We always have the corresponding index factorial. And then what we are missing for the coefficient is giving the idea that we're going to be alternating between 1 and negative 1. So, of course, we're going to have a negative 1 to the power of something, and we want it in such a way that multiples of 4 plus 1 give me positive, and multiples of 4 plus 3 give me negative. And this we can achieve it just by considering this exponent k. Let's check here. When k is equal to 0, then we are talking about the term that corresponds to 2 times 0 plus 1, so it corresponds to 1, and that one is going to be negative 1 to the power of 0, which is 1, as we wanted. This is what we have over here. When k is equal to 1, then we're going to be talking about 2k plus 1 even being equal to 3. So we're going to have not negative 1 to the power of 1, which is negative 1. And this is corresponding to multiple of 4 plus 3. So that index is what we need to make alternate from positive to negative. Now, the question that is left for you is to check for which values of x this series is convergent. And you should try this, and then you can go to your formula booklet and check that the series is actually there.